So welcome again to all of those for another WMCTC evening lecture, sixth form lecture. And I'd like to thank, first of all, the WMCTC and the Royal Society of Chemistry, as well as the University of Birmingham, for making these or enabling these lectures, and for funding as well. And it gives me great pleasure to introduce our evening speaker, Professor Stephen Liddle, who is the head of inorganic chemistry and the co-director for the Centre of Radiochemistry Research at the University of Manchester. And his presentation, I'm going to say the title in a minute, is going to cover uranium, which is a very topical element at the moment as we look to nuclear fusion to perhaps decarbonize our energy and the environmental benefits from nuclear energy as well. But just saying the word uranium obviously polarizes the audience, as people have a lot of preconceived ideas about the element. So is it a force for good or otherwise? And so the title of this talk is Uranium, the Bogeyman of the Periodic Table, a case of Dr. Jekyll or Mr. Hyde. So I'd like to thank and introduce our speaker once again, Professor Stephen Liddle.
Thank you, Mark, for the very kind introduction, and good evening, everyone. Shame I can't be there in person, but I guess it's the nature of the world we live in at the minute. Maybe the next time I'll be able to be down at Birmingham like the last time, which was a couple of years ago now, but feels like a lifetime ago. So yeah, I do a lot of research on uranium. It's basically my favorite element in the periodic table. But clearly it's an element with something of a PR issue in terms of how it's viewed. And so I'm just going to talk through a variety of issues surrounding uranium, its role in the wider world. And I'm going to try and convince you that fundamental research can actually contribute to sorting out some real world problems that we've got. I just want to emphasize, I'm not here to try and convince you that nuclear power is the answer to everything. I'm just going to give you what I think are unarguable facts, and I leave it up to you how you interpret them and how you conclude them. And I think that the opening slide kind of sums uranium up really. On the left-hand side, as soon as people talk about nuclear, and of course uranium is synonymous with nuclear power, straight away you see images like this. This is the kind of image you often see associated with stories about pollution, but actually what's coming out of those towers is water vapor from cooling, but often it can be misrepresented. On the other hand, is clearly something much more disturbing, which is a rendition of an atomic bomb after it's gone off. And one of the reasons I picked this is because in some really weird twist, it sort of looks like a clown laughing at you, which I'm not really sure how this happened, but I mean, this is just one of these strange things in life. Now, why can't I advance slide? Oh, there we go. Right, so I do view uranium as being a very split personality element because of the uses that we've given to it. On the one hand, we've got Mr. Hyde, who's not a particularly pleasant individual to run into. We opened Pandora's box around about the time of the Second World War in the last century, because there was a race to generate atomic weaponry to bring the World War to an end. And so then things like this is what erupted out of that Pandora's box that we opened. And of course, once we opened that box, we could never close it again. And then we had the arms race and the war as a consequence. And of course, it's a hugely destructive event. But actually, bizarrely, it's a way to make new chemical elements, which is something I will come on to in a little bit. Another aspect of Mr. Hyde is this. Now, this is a picture of Fukushima, the power plant out in the east that kind of had a major problem when the tsunami hit a few years ago. It's really difficult to find an in-focus version of this photograph, and that's because no journalist in their right mind wanted to get any closer to actually then take the photo appropriately. And of course, what was going on here was there was a catastrophic failure of the reactor as a consequence of the tsunami, and then apparently there was a meltdown and all the consequences that come with that. But that's a pretty severe instance of when things can go wrong. And also, however, on the other hand, it is arguably the case that nuclear power can be quite good in terms of our CO2 footprint and having sustainable, secure energy supplies. And of course, nowadays you can go out and get your own nuclear reactor on the internet. You can order the Joy snap together reactor. It's not that expensive, easy to put together. But I think actually they advertise a flaw in this. So if you look at those two kids, if you see the flash in that building behind them, I'm not sure I would be standing there trying to fly a kite. Okay. So over the years, uranium's reputation has been up and down like a yo-yo. When people first became aware of it in a kind of a regular sense out in popular culture, it was actually a bit of a fad element. So people would go prospecting for it, and a little bit like a gold rush. There was also a uranium rush. People just sort of found this element very exotic, and they would go digging for it. Apparently it and other elements like thorium were put in toothpaste, and the advertising claim was that it would make your teeth be white and sparkle, not like what we do nowadays with tooth whitening, but basically this was something that people tried to commercialize. And I'm really not sure about the one on the right, but apparently you could get your ice cream with a sprinkling of uranium on top. I really cannot imagine that was nice. PR and science. And I think most people, one way or another, at some stage, even if they don't realize it, they've seen photographs of uranium glass, which of course glows when you shine a light on it. And this is, I think, is what underpins the classic cliched comment about if things are radioactive, does it make you glow in the dark? I think that's where this comes from. Although in the century gone and running up to now, the tide really turned against uranium, really mainly because of its association with nuclear, be that weaponry or for peaceful civilian energy production. And actually, there's probably no one thing on the planet that's done more damage to the public image of uranium as an element, but also nuclear, and that will be The Simpsons, because of course, it's a perfect blend really for negative PR in terms of Mr. Burns, the evil boss running the plant for all the wrong reasons, Homer is the incompetent person who's going to let everything melt down. And then, of course, there's Bart, who finds Binky the three-eyed fish in the local river. I should say a three-eyed fish could occur naturally. That's called evolution. You would just argue in this case that the radioactivity has accelerated that process. But of course, the knee-jerk reaction is that, oh, this is really bad, therefore we should stay away from it. Now, nuclear does have real problems, okay? They're not made up, they are legitimate. And the main problem is the vast amount of waste that is generated by the process of doing nuclear fission. And that's because you end up with this mix of stuff coming out the other end that's very difficult to separate. And often you have quite small quantities of incredibly radioactive materials dispersed in a much larger volume of actually non-radioactive or very lowly radioactive materials. But overall, you have something that's a real concern. And so this is a stock footage from a storage area. I think this is low-level waste, but basically there's a lot of it. And of course, very publicly, widely known, there have been real issues in terms of catastrophic accidents in nuclear power plants over the years. That there is a picture of Chernobyl. Well, it's important to emphasize that normally there's extremely extensive arrays of engineering safety systems put to this kind of thing, but that's a very good example of what happens when you circumvent those engineered systems to try and do something that you might describe as being outside the spec of the plant. So you might quite reasonably say to yourself, well, why did we ever get into this in the first place if it's such a difficult, awful thing to work with? And of course, the answer is it was political. So around about the time of the Second World War, was over, the UN is getting going, the Security Council is being set up, huge drive for the UK to be on that Security Council for all sorts of geopolitical reasons. And so we engaged in the race to obtain nuclear weaponry to get ourselves a prominent role within the UN, and we were successful in doing that. The consequence, though, of that is that we then have a lot of places where we've been generating nuclear materials, and could we then use them for something quite sensible? And of course, the answer then is civil energy. And going back to the previous slide, you might argue that one of the reasons we have these processes that generate lots of waste is you might argue that the science to produce materials for weapons to get that goal of being on the UN Security Council was that the politics pushed the science faster than the science was comfortable to go at. And so it was almost like it was forced to go forward, even if you might argue it wasn't really ready to go, but the imperative was to get the materials to make the weapons to secure the seat on the UN Council. But nowadays, we're using about 20%, about 20% of our energy breakdown is nuclear power. Ironically, it's slightly higher up in Scotland, even though the SNP are an anti-nuclear party, but we average out about 20% for the UK overall. And actually, there was an article on the BBC News website today about these new SMR reactors that are going to be rolled out by Rolls-Royce. And I was looking at the breakdown of the energy production there, and it's looking pretty similar still to this table. So even though this table's getting a little bit out of date, we're still quite reliant on our electricity from nuclear power. And the unpalatable fact is if those plants don't operate, people's lights go out. And so this is at the moment an essential part of our energy mix. Whether it should be is an entirely separate matter. I'm purely talking here about the practicality of that this is an essential component of our energy mix. And actually, coming back to Mark's opening comments, and some of the comments I've alluded to are being more so far, the fact of the matter is that as a species, we've had a pretty profound effect on the Earth's climate. You can track CO2 emissions right back to the advent of the Industrial Revolution. And so there's serious questions here about when we're producing our energy, which is a society we demand, and it would be a very brave politician now who would stand up and say to be environmentally friendly, we're all going to have to accept the electricity being off a day a week or something like that. We have this insatiable demand against what the impact of that on the planet is. And in terms of production at the point at which electricity is generated, nuclear actually stacks up pretty well. Although, like a lot of things in life, you should really be looking at the process in the round. And I would say that what you cannot ignore is the phenomenal CO2 footprint in the concrete used to produce these plants. But then you might argue there's a lot of concrete and a lot of other processes that generate electricity. So it's a very complicated problem. But the bottom line is if you've got a plant that's there already and it's working, then you're not generating CO2 or any significant levels compared to other technologies every time you're generating the electricity that's used by you, the consumer. So there is a role there for it, but again, there's bigger decisions about whether it should be a role. Now, what I come across a lot is people who are either completely okay with nuclear, they don't have a problem with uranium, or people who are right at the other end of the spectrum who just instantly recoil and really don't like it. And I found myself wondering for a while, why was this the case? Why does it generate such a visceral reaction? Now, it's easy to answer if you're thinking about weapons. It's a bit more of a complicated issue, I think, when you're thinking about energy production. But actually, it really boils down to a very simple thing. So apart from the startling fact that uranium and nuclear is actually synonymous with Marmite, we are vehicles to reproduce our DNA. Because DNA is a very unreactive molecule, and so it's ended up accommodating itself in our bodies to be reproduced. But DNA is very savvy. It knows what is not good for it, and it knows that radiation is very bad for it, because DNA that is damaged will either be mutated or will not be able to reproduce. And so it's hardwired in us to recoil from things that we intrinsically know are going to harm us, like a fire or radioactivity. But again, this is a very complex issue because most of us have no problem going and lying on a beach and irradiating ourselves for several hours to get the perfect tan. But actually, you're exposing yourself to significant quantities of radiation. If you get in a plane and fly somewhere else on the planet to go on holiday, as soon as that plane gets high up into the atmosphere, you are receiving a higher dose level of radiation from cosmic rays and the like. And if you go down certain cellars in Cornwall, you can come across radioactive gases that just happen to be there. So this is a natural phenomena, but we are programmed to recoil from it automatically. And that's why we tend to get this visceral response when we deal with this topic in terms of radioactive elements in the periodic table, but also their applications. But I always put this slide in because I think it's a very important thing, if you've never had the time to stop and think about it, that once you grasp what's going on and you understand why you are fearing something or recoiling, then you can start to think about what that really means and whether you think that response is still appropriate. It might be, but you might be in a scenario where actually when you think it through, it's not appropriate. Now, uranium sits in the periodic table. If you're a physicist, a cosmologist, you're thinking about things in the bigger universe, you only really need to worry about two elements in the periodic table, and that's hydrogen and helium, because they are the main constituents of stars. But as soon as you get down to planetary level, then thankfully, and I'm very thankful for this and an inorganic chemist in the world, we've got this huge array of elements from the natural world to play with in terms of organizing them in different ways to make new materials, but also categorizing them and understanding why they sit where they sit within the periodic table. Now, obviously, uranium's down at the bottom, it's element 92. It's actually a very significant place in the periodic table because uranium is the last element in the periodic table that occurs in any significant level naturally. Once you go beyond uranium, you're into the realm of elements that even if they are formed in nature, they're there in incredibly small quantities and then they decay away through radioactive decay, or they have to be synthesized by humans. Otherwise, they would not exist in the universe. Okay, there's another, I think, very beautiful way of showing the periodic table, and this is from Mark Winter at Sheffield, and this is showing the periodic table in terms of atomic orbitals. So if you're studying your A-levels, you'll have come across s orbitals for the s blocks, so the alkaline metals and the alkaline earth metals. You'll have become familiar with p orbitals in the main group elements. And you've probably started to come across d orbitals on transition metals, which is the block of the red and the white sat in the middle. What you may not have come across yet are the lanthanides and actinides sat at the bottom of the table, and they use f orbitals, so they're often referred to the f block. And what happens as you go from S, P, D, and F is each time you're introducing extra nodal plane, and these orbitals get more complex as a consequence. And the way I often think of it is you're getting an extra degree of dimensionality when you step up. So the p orbital is kind of twice an s orbital, the d orbital is about 4 times, and then the f is ramping it up again. I just think they're beautiful things to look at because these are the shapes of the orbitals that nature has chosen to house electrons in, and it's electrons that do chemistry. The atoms are the ringmasters in any molecule. They're holding on to the electrons, but it's the electrons that actually execute chemical reactions. And so I just think it's fascinating that these are the shapes of the orbitals that we have, but they're very particular, peculiar set of shapes for the F elements at the bottom of the table. And this gives them all sorts of unusual properties. And quite often you see the F elements behaving in a very different way to pretty much the rest of the periodic table. Or at the bare minimum, they're very different to the D transition metal block sat in the middle, and yet they're all metals. And so it's the nature of the electrons in these orbitals which is transforming the way that these elements behave. Now, I mentioned a little bit there about uranium being the last naturally occurring element in any particular significant level in the periodic table. I just think it's helpful to get some historical context. So uranium was discovered in 1789 by Clathrow. This was in the era, what I often refer to as the Age of Wonder, where the human race was discovering new elements all the time. We didn't quite have the periodic table at this point, but I think it would have been a truly remarkable era to have witnessed in terms of people discovering the foundations of matter in terms of new elements on a regular basis. Just a few years later, in 1794, Gadolin isolates yttria, and this was the classic example where thought they had one element. Turns out it was multiple elements all co-crystallized in the mineral. And they all discovered it at Ytterby, which is a very famous place in the world of chemistry because it's got no less than 4 of the lanthanide elements named after it. So it's the place in the world with the most number of chemical elements named after it, which is quite a record. A little bit later, Klaproth is at it again. He's discovering the early lanthanides in the periodic table. Then thorium is discovered. Then protactinium is discovered. And this is an interesting point from 1913 to 1916, because then comes the recognition of different isotopes of the same element, which have radically different half-life times in terms of their radioactive decay. And then you draw a line, because that's when the era of element discovery, and when I say discovery, I mean of things that naturally occur, essentially comes to an end. And then we enter an age of element synthesis, where the human race now has it within its power to start to synthesize new chemical elements. And whenever I think about this, I think this is truly remarkable that we as a species have acquired the ability to generate new elements in the periodic table. We are basically being God elements out in the world and the universe, and we have that power. And it starts with the synthesis of neptunium, and that was really a stepping stone, as I'll mention in a moment, to obtaining plutonium, because that was the chase for an atomic bomb. And war is the classic example of generating technological change in an incredibly rapid rate. Quite often, it's war that gives you a really fast burst of technological advance because there's a real imperative. And this was exactly that kind of example, that we stepped off from discovery into synthesis because there was a big drive behind it, which was to get the weapon to bring an end to the Second World War. And then people, in particular Seaborg, as I'll mention in a minute, start to work their way along, literally creating the new elements that will build up to be the actinide series, moving their way along. And this is quite time-consuming stuff. If you're playing God with the chemical elements, it doesn't just happen overnight. It takes time to get these things right and to figure out how to do it. And this comes right up to the current day. We are still making or trying to make new chemical elements in the periodic table. We're sort of up to about element 118 now. There could well be more. There are these islands of stability in atomic theory, that certain ratios of protons and neutrons will give you stable isotopes. So there's a principle that we could go to really high atomic numbers, but it becomes really technologically very demanding work to do. And some of these elements, there's only been a few atoms of them made at once on the face of the planet. And so this is devilishly difficult work to do. But just very briefly, I just want to touch on something, which is the abundance of the elements. So the lanthanides, which is that top green row, are often referred to as rare earths. And this was a historical mistake, that the difficulty of extracting things was confused with their terrestrial abundance. But the next green row down is the actinides. And that first tall green pole on the left is thorium. The next one's protactinium. Then the next tall pole is uranium. And then back to my earlier point about it's the last naturally occurring one, you see how that series flatlines. So although they exist, they're in very small quantities on Earth compared to all the other elements higher up in the periodic table, which have much bigger abundances. But uranium, for example, is about as abundant as tin, and we've been mining tin out of Cornish mines for centuries. So there's enough of it on the planet. It's just a question of what we do with it. Now, the reason, of course, why there's never much of these highly active transuranic elements at once is their radioactivities. And this is a wide span, it's isotope dependent, but some of them have incredibly long half-lives, tens, hundreds of thousands of years. And this is why a lot of these elements, if they're generated out the back end of nuclear power energy production, have become such an issue because they don't just go away overnight. They're going to be there for generations and generations and generations, which then brings interesting questions about if you decide to bury them in the ground, how are you going to make sure that that facility is still keeping everything contained, not just in a few decades' time, but hundreds of thousands of years' time, potentially. And so these are really big questions for people to grapple with. Okay, so of course, for a long time, uranium was just another element in the periodic table, but it was the discovery of nuclear fission which really brought it into this regime where good and bad applications of it were dreamt up. And so this is all kicking off in the run-up to the Second World War. Now, Fermi and Nodark had done a lot of work on predicting nuclear fission. So this was a known concept. And then it was actually done for real. But a lot of people, they were kind of scratching their heads for a while because they were trying to understand how barium was coming out of something that had uranium input to it. And this is where Lise Meitner came into the equation because she realized what was going on. And she worked with Otto Hahn on this. And then this is just one of these travesties of history. Meitner had to flee from Germany because of the Second World War, and she went up to a Nordic nation. And for intensely political reasons, Hahn published the resulting work without Meitner as a co-author, and that meant that she missed out on the Nobel Prize, and so he got it, but arguably it's her that did the majority of the work, so it was a true travesty that she was missed off the Nobel Prize, and it was all because of what was going on in the Second World War. So then people are interested in making elements past uranium, especially for the weapons applications in the Second World War, but also thinking about energy production later. So how do you do that? It's actually fundamentally very simple. Imagine putting a football on a stool in a room, say about 20 meters away from you. Then imagine picking up a marble, and that's your neutron. And you're going to throw that marble at the football. And you need to throw the football just the right speed that it doesn't bounce off and it actually goes in and sticks. And this is fearsomely difficult to do. And so basically it becomes a numbers game. They invented these cyclotrons, so-called atom smashers, because that's exactly what they were doing. They were picking a target, which was a chemical element, then they were firing atomic particles at it with huge flux rates because the hit ratio was so small. But the bigger the flux, then of course, after some point in time, you're going to get some hits. And if you give it long enough and your flux rate is high enough, then you're going to convert a sample into a brand new element. And so in some ways, an elegant process, in other ways, a very blunt way of synthesizing chemical elements, but it works. And so this was what was pushed at the time over in Berkeley in California. And so the first target was neptunium. So that's stepping off from uranium. And basically a neutron was fired into uranium-238 to make uranium-239. Of course, there's a bit of gamma coming out at this point because this is a high energy process. But what would happen then is the 239 would transmute into neptunium-239 with beta emission. And so what's going on here is that the atomic number of that element is then changed by 1, which is why it's switched over to be a new element. This is very difficult stuff to do. And of course, when you've got a new element, you have to characterize and try and convince yourself that you really do have a new element. This is quite tricky stuff to do if you're working on very small scales. And there was a lot of confusion at this point as well, because actually, before all of the actinides were recognized, there was some ambiguity about what uranium really was. No one actually knew that the actinide series existed underneath the lanthanides. So at the very beginning, uranium was misclassified as a transition metal because it shares a lot of properties with group 6 metals. So in the periodic table in group 6, you've got chromium, then molybdenum, then tungsten. People thought that uranium was just a heavier version of tungsten. Little did they know that it wasn't a D transition metal, but it was an F actinide metal. And that's the difference between them. But no one knew that that series of elements existed. So it's perfectly reasonable to think, oh, these just must be more transition metals. But people started to suspect that something different here was going on. And that was because the elements weren't quite behaving the way that I think people expected them to behave. And so this guy, Edwin Macmillan, was involved in a lot of this. Now, uranium had been named after Uranus, and there was a big trend at the time to name things after planets. So element 93 was given the name Neptunium in honor of Neptune. But this was a halfway for the real bit, which was plutonium. And this chap down on the right, Glenn Seaborg, was really making a name for himself at the time. He was basically intent on making element after element after element that was new. And of course, that really gets you noticed when you're making new elements in the periodic table. This, again, this is, bear in mind, this is during wartime. He was very fixed on this aim that they needed plutonium because it had already been predicted that it could underpin an atomic bomb. So they needed enough material to test it. Macmillan was volunteered and moved over onto this work because of his prior experience. And so then they got together and got on with it. And so they made some Neptunium from bombarding uranium with deuterons. And then that decays to give you plutonium-238. And so then they had therein. And then this was developed a little bit further. And then this is back to Pandora's box. Past a certain point, they had enough material to test. And then all of the theoretical predictions were proven indeed to be correct because the US was successful in detonating a fissionability of plutonium-239. If uranium is the Jekyll and Hyde of the periodic table, plutonium is the Hannibal Lecter of the periodic table. Because it's an element that shouldn't exist. It's an element that nothing that is evolved in the natural environment of the world has ever come into contact with, and therefore we haven't developed physiological responses to deal with it particularly well. So it's incredibly lethal to almost anything that comes into contact with it. Although, as I understand it, some microbes actually can feed off plutonium and do very nicely off that, but that's a very niche case. I've got a little note at the bottom here. Well, there's a star on this paper. So it was received in 1941, the publication that said, right, hey, this is what we've got, but it was withheld for publication so that it didn't inform the enemy as to what they were up to. So this is another example where science was having to dance a very peculiar dance to fit in with geopolitical events going on around it. Now, Seaborg wasn't going to hold back at this point. He really had the bit between his teeth, and he could sense that he could go further and further. If they could leapfrog from uranium to neptunium to plutonium, then why not go one space further to the right, or another space, and keep on going? How far could you go? And the answer is that they could certainly go as far as making elements like curium and americium. This is 1944, and this is possibly one of the most bizarre ways that new elements have ever been announced to the world. There was no formal press release, there was no staged PR conference to announce the fact that there was another 2 elements in our world, Seaborg went on to a radio show called Quiz Kids. And the presenter, I think probably just, to try and get the discussion rolling, went, oh, so hey, Glenn, made any new elements recently? I bet you he wasn't expecting Seaborg to turn around and go, oh yeah, we made another 2. At which point the classifications officer is probably pulling his hair out, because now there's no point keeping these elements secret anymore, because Seaborg's just announced them on a national radio show. So that's probably got to be the most unorthodox announcement of 2 brand new elements in the periodic table ever. I imagine Seaborg probably got quite the dressing down for that afterwards, but basically it was too late at this point, and he'd made such a name for himself going this far. They weren't going to fire him from the job, and that was probably part of the calculation when he decided to announce them. And he was probably fed up with them not being announced, because they were brand new elements, but they didn't have any use in nuclear weaponry. So why wouldn't you tell people about them? Except it gives you a clue as to what you might have been up to with the elements in between uranium and these 2. And so they kept going. And next up were berkelium and californium. And just sitting under the title here, I think, is an astonishing piece of information. So first of all, you needed a kilogram of plutonium. That in itself was a major undertaking. You'd then take that kilogram and bombard it with whichever particular atomic particles would work, and you'd end up with 1 milligram of americium, or, there's a typo, that's not curium, that should be californium. But basically, terrible yields. I mean, if you were a synthetic chemist, you would never accept that as a workable yield. But if your prize is a brand new element in the periodic table, then you'll take it. And then there's a little bit of what I call the moon lander effect kicks in. Clearly Berkeley's very proud of making yet 2 more new elements in the periodic table. They've phoned up the mayor's office, look what we've done, and the response was just whatever. And it was a bit like everyone was looking at the first moon landing, everyone was looking at the second moon landing. They probably weren't looking at a few more down the line of the moon landing. So it was that kind of psychological thing where people get sick of something and move on. And so Ghiorso, as the guy working on this, was really quite upset, because I think he sort of felt quite legitimately quite aggrieved. I mean, do you not understand how much work goes into making a new element? And yeah, so this is the sense of humor at the time. He what did they call it? BM, because it was a bit of a stinker to discover, which is his way of saying it was really hard to make. And then the New Yorker, the newspaper at the time, suggested that UC Berkeley had lacked foresight and should have called the elements 97 to 100 universitium, orpheum, californium, and berkelium. Berkeley's response: they could not risk the New Yorker finding elements 99 and 100 and calling them newium and yorkium. So I guess that was where their humor was at the time. People really wanted to keep on going. Now it's Einsteinium and fermium's term. I mentioned right at the beginning, a nuclear detonation is actually a way of forming new chemical elements. And actually that's where the first Einsteinium and fermium were first detected. The second bullet point I find particularly intriguing if you stop to think about it. It was found on the filter papers that were flown through the cloud. Now just stop and think about that. How do you think a piece of filter paper got to fly through the top of an atomic bomb going off? There were no remote operated drones back there. Some poor air crew probably got the shock of their life in their morning briefing when they were told what they were going to be doing that day. Not something I would be wanting to do, given EMP cannot quite often knock out electronic apparatus, like say the electronic apparatus you need to keep an aeroplane flying. So this was really difficult stuff to do, but of course they were still trying to understand a lot of things, not least of which what goes on in one of these bombs when it goes off. But to their surprise, they discovered these new elements. There's since been much more efficient and much better for the environment ways discovered to make these elements in the periodic table. And I think also this is when the environmental aspects started to be realized by people. If people were finding fermium on bits of coral, this was a warning sign that this wasn't just playing around with stuff. This had much bigger implications. Then Mendelevium was synthesized in honor of Mendeleev, the godfather of the periodic table, bombarding Einsteinium with helium ions. I mean, this is the lengths you would go to. It's a question of what do you want your atomic number to be? What do you want, therefore, to combine to get the right combination of numbers that gives you a new element? And this bit I find remarkable. So they make this tiny amount of this new element, and they will go and jump in a car and drive around the Berkeley campus to the analysis room, making the samples up whilst in the back of the car because they just didn't have long enough to hang around. Why they didn't have the analysis room next to the cyclotron, I don't understand, but for some reason it was sited somewhere else. This is clearly in the days before health and safety, because I really don't think nowadays you'd get away with saying that you'd make a brand new element that's radioactive and jump in the back of a car with it and drive around a campus so you can get to the analytical suite. Okay, so now after Seaborg's work, there were lots of people involved in this, but Seaborg is the chap who was the theme leader. We have all these extra elements, and so there were question marks about where they should go in the periodic table. Because remember, I said no one really understood the notion that there would be an actinide series, or as you shall see in a minute, it was not widely known there could actually be an actinide series. So Mendeleev famously, came up with the idea of a periodic table, but he didn't know about the existence of an F shell because he didn't know about quantum chemistry, because quantum chemistry was not a thing when Mendeleev was thinking about elements in this periodic table. Moseley, though, was measuring the X-ray spectra of elements, and it's because of Moseley that we got to grips with the concept of atomic number. And of course, this is a fundamental clue to understand order periodic table. And what he discovered from his measurements was that there was these 14 elements, lanthanum to hafnium, and that is where your lanthanide series sits. But it wasn't until Bohr came along and thought about it that he realized that the fourth primary quantum shell can accommodate 32 electrons, because that's 14 more than the 18 you get from combining 1s, 3p, and 5d orbitals together. This then invokes the notion that there must be the 4f series for sure. But it wasn't really until Seaborg highlighted to everybody that now we had another group of elements, and that actually the actinide series, the 5f series of elements in the periodic table, really took form as a concept to essentially complete the periodic table, or at least complete it at the time, because now we've got extra super heavies added every now and again. This throws up quite an interesting conundrum. So if you look at the top line here with calcium and scandium and strontium and yttrium, there's no ambiguity about where those elements are going to go in the periodic table, because scandium is 3d1, so this is the elements in their ground state, and yttrium is 4d1, so they're clearly the first two elements at the start of the D block in the periodic table. But if you then look at the row starting with barium, you've got lanthanum, it's got a 5d1 configuration, but so is lutetium at the other end of the lanthanide series. If you look at actinium, which is 6d1, well, it's the same for lawrencium. So which do you put in group 3? Because actually either of those pairs could go in on the basis that they are a D1 configuration. Now, lots of periodic tables around the world put lanthanum and actinium under scandium, then yttrium. You hardly ever see any like the one on this slide, or I think we're probably starting to see them a bit more nowadays. But for a long time, and this is what Seaborg did, the issue is duct, where lutetium and lawrencium are just put as placeholders, and then you have two rows of 15 elements. Now, straight away, this is a problem because you're dealing with an atomic shell that only has 7 orbitals and therefore can only hold 14 electrons. And so that's 14 elements. And so you can't have rows of 15. Now, I understand why people sidestepped it. But it's quite interesting that for a long time, I think I saw, certainly as an undergraduate, a lot of periodic tables that put lanthanum and actinium in that slot. but there's actually quite good evidence that it should be lutetium and lawrencium, because when you look at the atomic radius, the ionization data, their melting points, and electronegativities, you always find that for the lanthanides, because this data is not easy to obtain for radioactive actinides, lanthanum is the outlier, but lutetium always fits the trend. And so there's a very strong argument that lutetium and lawrencium should sit as group 3 elements. I want to emphasize this is not a settled matter. Only 2 years ago now, 2019, the International Year of the Periodic Table, there was an IUPAC group set up to examine which element should sit at the bottom of group 3. And in the end, they decided not to really force it one way or another. And so you'll find all 3 types of periodic table in different lecture theatres around the world, some with LA and AC, some with LU and LR, and some with nothing there at all, and 2 rows of 15. So even now, in the year 2021, there's still a vigorous debate about where some elements in the periodic table should actually be, which I just think is fascinating. There's no doubt about where uranium should be, though. It's very safe where it is. Now, what most people overlook, though, is Charles Janet's left step periodic table. This is a huge shame. I'm a big fan of this periodic table. So he was around in the late 1800s and early 1900s, and he generated the periodic table in this form. It agrees perfectly with quantum theory before quantum theory existed. Each row corresponds to the Madelung rule, which is really nice. And he also put the actinides in the right place 20 years before Seaborg. But basically, Seaborg was much better at getting his message out. And so a lot of people missed this completely, which is a shame, because I think this guy was a genius, because he used this to speculate about elements with negative atomic numbers. He was in effect speculating on the existence of antimatter before anybody really knew that antimatter could be a thing. So this is truly visionary, that this guy constructed an alternative version of the periodic table, which to my mind absolutely nails it. And oh look, under scandium and yttrium are lutetium and lawrencium, which I personally agree with. And this then sets the scene for a G shell of orbitals, if we can ever make elements that far out in the periodic table. It, however, and this is probably the reason why it never took off, it's incredibly hard to show in one go because it's so wide. You know, any periodic table, irrespective over what decision you've taken about which elements going at the bottom of group 3, there's always the F block set out underneath. Otherwise, the periodic table would be too wide to conveniently represent. And that was probably the biggest downfall of Janet's left step periodic table, which is a true travesty, because I think this is, in my humble opinion, the best way to represent the elements in the periodic table. Okay, I'm just going to now, having given you a pretty quick tour of uranium, the bigger picture, how it sits in the periodic table, the elements around it, and the history of how all those elements came into being. I'm just going to now switch gears a little bit and talk about a few aspects of some fundamental science and hope that you can see what's going on. And I just wanted to show these pictures because uranium is not an element that you can just routinely order in a catalogue. In many ways, that's quite reassuring. So quite often we have to source our material in particular places. And so often, if you start a synthesis with a metal halide, you just buy that from a chemical company, whereas we have to make them from scratch. But it's not often that people actually see the colors of uranium compounds. And I just want to show them because I think they are truly gorgeous. You've got the bright emerald green uranium-4 as the tetrachloride. Down in the middle, you've got uranium triiodide. It is this gorgeous dark blue color. But then oxidize it by 1 to make UI4, and now it's a bright orangey red. These are the bright colors that you associate with transition metals. And of course, uranium was misclassified as a transition metal until Seaborg realized that, was very good at telling everybody that there is an actinide series. And so it's no wonder that uranium was misclassified, because you just have to look at it with the Mark I eyeball and you see something that is screaming transition metal, but it isn't, it's actinide. Show those uranium turnings down in the bottom left, because again, back to this kind of image that uranium has about glowing in the dark. Uranium metal looks like metal turnings when it's turned out because it's a metal, but you'd be surprised how many people think that surely it must glow in the dark, because that's what all the movies imply. But it's just an element in the periodic table. It's just what we've done with it, which has brought its reputation. Okay, so reasonably quick now for the next few slides, but hopefully you'll get the gist of why I'm mentioning them. So Fukushima had a meltdown. It probably wouldn't if it had a slightly different type of nuclear fuel in it rather than the standard oxide. There's been a lot of interest in nitride as a so-called accident-tolerant fuel. It's an interesting turn of phrase, because you'd like to think anything in nuclear was accident tolerant, but it's a bit more accident tolerant than the oxides. The traditional routes of making them can introduce all sorts of impurities, and that's a real problem if you're dealing with the fissionability of elements. But it's got some spectacular properties compared to the oxides that are used. Incredibly dense, so you don't need a lot of space. Quite a high melting point, higher, I believe, than some of the oxides that are used, so more resistant to a meltdown scenario, and absolutely outstanding thermal conductivity, which is really great, because when you generate the heat from nuclear fission, you need to get it out to then move it down the line to the turbines to actually generate the electricity. From a chemist's perspective, it's been fascinating for well over a century, because all the way back to Haber's original patent for the Haber-Bosch process for the synthesis of ammonia. Remember, the world makes multi-ton quantities of ammonia every year to make fertilizers. It's not an exaggeration that life on Earth would struggle to exist if we didn't have this process. But at the beginning of the second paragraph, Es würde nun in den Uran, it's talking about uranium. Turns out uranium is actually the best catalyst for making ammonia. It's obvious why we don't use it in a highly pressurized chemical plant. But even back then, there was a hint that uranium chemically is a really intriguing element. So for a long time, there was a lot of interest in making molecular uranium nitrides, which could then be studied, because sometimes you can study bulk materials, but sometimes it can be quite challenging. But if you make a discrete molecular complex, then you can study that molecule in great detail. And so this framework nitrogen atoms around the uranium is just an organic ligand, and we use that to generate a very particular pocket at the uranium where we can execute well-defined chemistry. And here that is when you add an azide to uranium-3, the uranium reduces the azide, you eliminate dinitrogen, and you install the nitride N3- functionality at uranium. And then the target for this particular work was to then take the alkali metal away and get the terminal UN linkage. This was something that people had been chasing for a long time, and various systems didn't work. We were fortunate enough to be able to make it work with the ligand system and the synthetic approach that we took, and with a highly talented PhD student who made this chemistry work. And so you get quite short UN distances here. So the reason I put that 1.825 bond distance is a carbon-carbon single bond is about 1.5 angstroms. A carbon-carbon triple is about 1.2. So for an element as massive as uranium, to have a bond to nitrogen that's only 0.3 of an angstroms longer than a CC single bond is showing you just how short that UN distance is. And because we had to link the story back, it turns out that nitride can be converted to ammonia. We've since shown that it can be hydrogenated. And so our argument, although this is a little tenuous, I admit, is basically it's a molecular model for what goes on in the Haber-Bosch process when dinitrogen is split to nitrides and then hydrogenated to make ammonia which is then released. And to my surprise at the time, I discovered, so Dave King was my PhD student. William Clegg was my PhD supervisor. He's like my chemistry father. Wheatley, a crystallographer, is my chemical grandfather. And so it turned out that Haber is my great chemical grandfather, which I found slightly ironic and amusing in a way, until I stopped and thought about it, that most can track back to a handful of chemists in the 18th century. But not everyone tracks back to Haber, so that maybe it was in the stars or something that I was going to end up making uranium nitride. Okay, but what my point here is we can make molecular species and probe them and understand their chemistry and then relate that to things that are going on megaton scales in chemical industry, not involving uranium, but with a well-known reaction that over a century ago was recognized as being the best when you do it with uranium. And now with computational methods, we can visualize the electrons in these systems with a process called density functional theory. We don't need to go to the ins and outs, but basically you compute the electronic structure of these molecules. And there on the top left is an F electron computed in the computer. On the top right, we have the nitrogen sigma bond to an F orbital on uranium. And on the bottom two, we've got nitrogen pi bonds to uranium, again using uranium F orbitals. This is basically an inorganic nitrile, but we can compute this and actually see what the orbitals look like in the chemical bonding of some of the heaviest elements in the periodic table. Moving on to another topic very briefly. Again, it's back to this big picture of what are our natural resources and how do we use them. We've become very reliant on crude oil. There is an alternative to crude oil if you don't have ready access to it. So for example, South Africa uses Fischer-Tropsch extensively, but essentially you're taking things that are given to you by nature and then reorganizing them into a particular way. And in the context of crude oil, it's distilling out all the components that you want, and then maybe you will do further synthetic modifications to various fractions to get a particular molecule that you want. With Fischer-Tropsch, you take CO and H2 and you get a wide variety of organic products coming out the other end, and these can all be separated out, but a lot of them are basically liquid fuels. The problem here, okay, so the problem with crude oil is it took nature millions of years to put it there, so it's not readily replaceable, and when you get out of the ground, you have to distill it. The problem with Fischer-Tropsch is it works, but you get a huge array of products coming out the other end and they all need to be separated. And this costs you time and money, and that's not particularly environmentally sustainable either. Now, no one's ever going to use what I'm just about to show you on the next slide, but it just illustrates the chemical power of an element like uranium. That if you take that uranium molecule on the bottom right and place it under carbon monoxide, each uranium gives up an electron and the carbon monoxide is reductively coupled to what's called an ethyne dialate. So it's got a 2- charge, one on each oxygen. And there's crystal structure of our product, which shows, because there's the picture of it, that we've made this species. And if we then treat it with an electrophile, in this case, silyl reagents, we spit out the coupled CO now basically is a protected molecule with those silyl groups. And that uranium-4 halide can be reduced back down, and now you've closed basically in principle, a catalytic cycle. And this is selective. Now that alkyne goes on to do something of its own, which it makes a substituted furanone. That's two of the alkynes coming together. What I've shown on the top right there is the carbon-13 NMR spectrum when we used C13 labeled carbon monoxide. And so we get these gorgeous NMR spectra when you can see carbon-carbon couplings and work out which carbon is which in the ring based on their chemical shift and splitting patterns. And so any of you doing A-levels, you'll have started to come across NMR and understand that in proton NMR, you get different multiplets depending on how many hydrogens are coupling to each other. This can happen with carbon as well if the abundance of the C13 is high enough. But the point about this system is using one well-defined uranium molecule, CO, and a protecting group, if you like. We've selectively made one organic molecule, but we haven't made 15 or 20 molecules that need of different types that need separating out, like in Fischer-Tropsch. So this is a specific reaction. We get only this product out every time. Now, if you want furanones, that's great. If you don't want furanones, that's not a lot of use to you, except that ring there, that's not a million miles away from being a sugar. And then that could be opened up and functionalized. But the basic point is you stitch together a C fragment. So you have a butane type precursor. So you're upgrading your carbon from being a C1 precursor to a C4 product. And of course, that's what Fischer-Tropsch is trying to do. And then lastly, I couldn't ignore nuclear power in general. There's a lot of reactor types out there. The uranium goes in a fuel rod. It's typically about 3, maybe 5% tops enriched. That is then burnt through. It goes through its fission processes. It generates a variety of elements there. Then it has to be dissolved up to try and recycle out the different components. And this is where the challenge is, certainly if you want to make nuclear more sustainable, to be able to recycle materials that are going in away from, let's call them the decomposition products from the radiolysis. If you can get rid of them, you could start to recycle things and increase the longevity of your fuel stocks. This then brings us to Purex, which is one of the most famous separations protocols in the world. You take your fuel elements, you dissolve them up, you get rid of all the elements that come after plutonium in quite an efficient step. Then you've got a mixture of uranium and plutonium. You selectively reduce the plutonium down using a weak reducing agent that's not strong enough to do anything to the UO2. And then in principle, you've got 2 separate product streams. But there's a dirty little secret of this process, which is the neptunium cross-contaminates both streams because it sits between the 2 elements. So it's a little bit like uranium and it's a little bit like plutonium, but it's actually its own element. But this means it's ending up in both streams. And how could we make that step a little bit better? This is actually a project we're working on with NNL. And what sits underneath this is that if you have an actinyl molecule, so over on the left, a metal with 2 oxos, 2 of them can come together when they're in the +5 oxidation state of the metal ion, and then they disproportionate via this process in the red box in the presence of acids. And we had some pretty strong acids in those separation processes. And then you get disproportionation coming out the bottom. You might say, who cares? Well, you should care because that helps the cross-contamination to occur. But also the hexavalent proportionation is very soluble and so environmentally incredibly mobile. So if any of this got out, it could be miles downstream and you would never know about it unless you went looking for it. The +4 oxidation state metal ions precipitate out, and then you would have immediate and obvious contamination at a point of a leak. And so this is quite a lot of concern about how to deal with this. And just very briefly, just going to show you that, again, using particular organic ligands around metal ions, we can control the chemistry and selectively reduce uranyl down from uranyl 6 to a mixture of uranyl 5 and uranyl 6. That's the molecule on the right-hand side of the slide. And when we take that remaining chloride away and reduce it again, we get this dimeric species here, where you've got these bridging oxygens. And this is synonymous with that process going on in the red box, because if you take that molecule and add in acid, it disproportionates. But if there's no acid, it's stable. And so by probing the fundamental chemistry, we're trying to get to the bottom of what would actually go on. In the not too distant future, you'll have noticed this is uranium, not neptunium. We intend to then, having learned our lessons from uranium, do this with neptunium for real and see if we can gain some insight into what's going on, what the problem is and how to fix it. And that's fundamental science trying to address a real world problem. So I'm just going to wrap up now on my penultimate slide, which is there's a lot of waste and other problems and processes that surround these elements in the periodic table, and especially uranium and also plutonium, it has to be said. But I don't think we've got enough knowledge because, as I said, the processes were pushed on probably a bit quicker than the science base would have liked because of the overarching political issues. And so we need to know more about these elements in the periodic table. And the way you do that is by doing fundamental research, because then you really get to see what makes these elements tick, what makes them do various things, and then you can try and design things rather than just relying on serendipity. Okay, so that's been a bit of a whistle-stop tour through a wide variety of things, but I hope it's given you a bit of flavor for uranium as an element, how it sits in the periodic table, and all the things that surround it. I just want to very briefly wrap up by saying, although it's well and truly stalled because of the COVID-19 pandemic, I'm passionate in outreach. It's one of the reasons I'm here tonight. We've been putting together a series of videos at Manchester in a project called Camera Chemistry at Manchester Explains Research Advances, where we're trying to explain what science we're doing and why it's important. So if you're interested, I think it's probably quite easy to find on a Google search. Go have a look. I'm going to stop there. I'm going to say thank you all for turning up virtually tonight and listening to me, and I will obviously be very happy to answer the questions that I'm expecting are in the comments feed. So thank you very much.
Excellent. Thank you very much, Steve, for that really really interesting talk, and covering all the aspects of uranium as well. It's interesting, people think it's just in the realm of sort of physicists and engineers, but there's a lot of chemistry there. And it's a very interesting point when you mentioned Lisa Meitner's discovery of the fission process, and actually was the skill of the analytical chemist in actually determining the very small amount of barium that was in their samples to actually underwrite the theory. So a lot of chemistry there.
Absolutely.
Speaking of chemistry, one of the first questions we had is a question for you. What sparked your interest in uranium before you saw your genealogical tree? What sparked your interest in uranium?
So I did my A-levels. I went to university, was an undergraduate. I did a year out in industry. It was a great year out, but it convinced me I didn't want to work in chemical industry. So then I decided to go and do a PhD, and that was in alkali metal chemistry. Once you've got your PhD, you can become basically a contract researcher. And that's the zone where you have to survive on contracts before eventually you might be lucky enough to get an academic position. And my first job I did was working on group 2 metals. So I had the S block well and truly nailed by this point. I then moved on through a variety of other postdoc positions. So I was actually a postdoc for about 7 years before I became an independent academic, and that's an unusually long time. It was just a lean phase of academic recruitment in the UK. And I got experience around the vast majority of the periodic table, except noble gases and the actinides. And I was thinking about when I was applying for positions to get into academia, and what got me into academia in the end was the award of a Royal Society University Research Fellowship. So every year, the Royal Society awards about 32 of these fellowships to people across natural sciences to get new blood into academia. And I was sitting there thinking, how am I going to be different to a whole bunch of other inorganic chemists who are all going to do fantastic work? How am I going to stand out from the crowd? And I thought most people will be working with S, P, or D elements. But by the end of the day, the selection panel will hopefully have either loved me or hated me, preferably loved me, but they'll probably remember the one crazy guy who wants to work on uranium as opposed to all the other transition metal chemists. And although that's a slightly cynical way of describing it, I did have a bit of a thought like this, that I needed to do something that was clearly different. That worked. There was another element to it, which is as a postdoc, I was always surveying the literature for what was going on in case it gave me an idea for a research fellowship to be funded on. And I just became aware that there was some very interesting stuff going on with the actinides. And so my timing was just right, basically, but that's why I picked it. I had a hunch it would be interesting. I could see signs of that in the literature. and it was a way to be different to everybody else, because I think quite often if you are doing something different, you're going to discover things that no one else is going to discover.
Excellent, thank you. No, that's an interesting point about standing out, and serendipity as well playing part of the career. That's very true. Another question here. I think in one of your earlier slides, you put some half-lives of some elements. And one of the isotopes was the protactinium-231 that had a very exceptional long half-life. The question is, when half-lives for this type of isotope are so large, so long, how do you actually calculate the half-life?
Well, you know, it's going to be an exponent. So you only need a few data points before you can extrapolate out, because you're absolutely right. You know, the human race has not been measuring the T-half of protactinium over 20-odd thousand years or whatever it is. But, you know, at the end of the day, these decay processes follow very well-behaved exponential processes. So it just becomes a matter of mathematically modeling them. I say just, you know, I mean, it's not like that's a walk in the park, but you know, this is where the power of mathematics comes to the discipline of chemistry and basically sorts it out for you.
Actually, talking modelling, I was very pleased to see, as a computational chemist myself, your slide where the modelling was in such good agreement with experimental, and also suggesting the mechanism. It's very interesting to see the two. And just to comment on the modelling, it's yes, it's again, people have disputed the results of modelling, and I think when it first came onto the scene, it may have been oversold slightly. But certainly computational chemistry, when you're dealing with those 5f electrons, is no mean feat. You're trying to solve the Schrödinger wave equation, make approximations, and for that many electrons, computationally, it's a huge challenge. So this is also one area that's advancing as we have more powerful computers as well. So it's really interesting to see a little bit more modelling effort on those actinides.
Yeah. So something I didn't want to get sidetracked with today is, of course, these elements sit in a relativistic regime, which is a really big deal. I mean, it profoundly changes their chemistry. So relativistic effects in the periodic table kick in round about Mercury. It's actually relativistic effects why Mercury is a liquid rather than being a solid metal. And it makes the F electrons behave in different ways to what they would without the relativistic effects. And so you have to go away and understand some of Einstein's scribblings to understand what is going on here. But it profoundly changes the behavior of elements in the periodic table. And you know, hydrogen is subject to relativistic effects. It's just the weighting scheme you'd attach to it is so tiny, you can dismiss it. But by the time you get to heavy elements in the periodic table, it becomes a big deal, because electrons are zooming around at like 2/3 the speed of light, which is jolly fast.
Excellent. There was quite a general question here that's I think we could spend all evening discussing, but there's a question as to what extent the UK has invested in uranium and nuclear power. And I think you sort of answered it, that politically we started off with the Tubalos project and some of the early research, and it was the military application that drove the choice of fuel for the civilian area. But it's waxed and waned throughout the years. But maybe you can put some comment about where we've gone and perhaps where we're going to go.
I think, well, I mean, the answer is the UK's invested an enormous sum. I'm not even sure I could put a number on it. There's a real pressing issue. I mentioned earlier in my talk, there was a BBC News article on their website today about this announcement about Rolls-Royce building these SMR reactors, because they're much smaller. And the numbers I saw quoted in that news article today was where a traditional nuclear power plant might cost you 23 billion to build. One of these smaller units could come in as little as 2 billion. Now, it's not like 2 billion is a trivial sum of money either. But those are the kind of sums of money that get involved. And then this is why it becomes quite contentious, because you get into all these debates about, if it's that expensive to build, how much is the consumer being charged for their electricity bill? who's going to build the plants? It's an enormous financial injection. And, there's been a variety of nuclear projects in recent years that have been cancelled because they were just going to cost too much. So there were concerns over national security, because often the government's approach is to get third-party companies to do the cash outlay in the first place. And then that starts to bring in issues about, if China is hugely invested and they've got Huawei technology, are we going to accept this? But yeah, it's phenomenally expensive. The price for it, if you like, is that you're then getting electricity on demand with no CO2 emissions at that point. But then the sting in the tail is you generate all the products, and that's very expensive to deal with as well. Mark, you might know the current figure better than I, but I think the NDA's estimate to clean up nuclear waste is it's well over 120 billion now, I believe.
Yeah.
But it's what's the phrase I'm looking for? I mean, there's an element of how much bang you get for your buck, but there's also an element of you get what you pay for. And the problem we have as a world, never mind as a country, is we've got ourselves hooked on crude oil. And it's entirely understandable why. It was there in the ground. We didn't have to do anything to produce it. We just have to extract it. And it's an extremely good energy vector. It's basically the best energy content vector of fuel that we've got. As soon as you move away from that, you're automatically going uphill. And so any solution that you derive is going to cost you an awful lot of money. It doesn't matter whether it's fuel cells, nuclear power plants, even wind turbines, which look like a fantastic solution. You need 10 kilograms of electromagnet per wind turbine. A substantial amount of that are lanthanide elements, which have critical supply issues because of the countries in the world that happen to be rich in them. Everywhere you look, there's a problem associated with finding an energy source that's good for the planet and reliable and isn't going to cost a fortune. So yeah, sorry, have I answered the question now? I've probably gone wildly off topic.
I think it's an interesting question. I think one of the key points I would say, you mentioned the figure there. When you look at the cost of nuclear plants, at least these days, when the costs are being proposed, they are including decommissioning costs, which wasn't known on the early reactors. And I think one of the key things now is there's such a great deal of transparency in the nuclear industry now, where there certainly wasn't in the kind of 50s when they're being built. But it's interesting to see. It'll be interesting the development of the small SMRs and how, rather than large construction project, you've got something that's assembled, built in a factory, constructed, and then just assembled on site. So interesting to see if that scales.
Yeah, so it doesn't get lost, because I don't know if it's come to you, but I've got a question in my direct feed. Does chemistry play a major role in medicine? And the answer is yes, because in radiotherapeutics, there's enormous interest in delivering radioactive elements to, say, a specific point of bone cancer to kill the cancer without doing harm to the patient. So although often we recoil from radioactivity, we can harness it to cure people of cancer if we do it in the right way. So yes, there's a huge amount of chemistry in medicine.
And actually, following on from that, you mentioned the Purex process as a way of reprocessing, extracting useful things from fuel. Could the Purex process be modified to maybe extract some useful isotopes from waste that could be used for medical purposes?
It probably could, because one of the very useful isotopes, especially because I had this one in my mind for treating bone cancer, is a particular isotope of samarium, which is one of the lanthanide elements. And if you can put that element in a particular organic molecule with particular functional groups on it, they bind to the calcium in your bone and lock it in place. And if you can direct it to the right place, then it's incredibly effective. I think also there's an isotope of lutetium, which is getting used as a medical isotope as well. I think in principle, the answer is yes, because there's all sorts in the soup of a dissolved fuel rod post-reactor, right? The issue is separating them all out. That's the challenging thing. So another point that I didn't want to get too sidetracked with is a lot of these elements, especially for the lanthanides, they are a very similar size. But they go on a very smooth gradation from lanthanum down to lutetium. But when the elements are very similar sizes, it by definition makes them very challenging to separate. We can do it, but then it becomes really expensive. And this is arguably one of the big challenges that a lot of people talk about in terms of dealing with nuclear waste. If you've got a tiny amount of material that's 99.99% of the radioactivity, isn't it great if with just one selecting agent, you could take that out of the equation in one go and do it selectively? Then you'd cure all sorts of headaches overnight. But there's several headaches to cure in any fuel rod that is dissolved. But actually what underpins your ability to do that is an understanding of the basic chemistry, understanding of things like chemical bonding, how covalently different ions bind, because you could generate different molecules that select for different metal ions depending on the tuning of the covalency and the bonding. And there's a lot of work been going into this over years. And the only way you can do that in a targeted way is to understand the nature of these elements, which is where you need the fundamental work.
Yeah, excellent. Actually, on that reprocessing process, you mentioned the accident tolerant fuels, the nitrides and carbides have been looked at. Would they require alterations to the reprocessing process? You know, are they dissolvable in the nitric acid, for example, or will they require adjustments to downstream?
Yeah, so earlier on when I said about you have to look at processes in the round, I think that's a classic example of that if you hone in on is it a more accident tolerant fuel, would it have better fuel performance? The answer is arguably yes. But then you look at how do you fabricate it? How do you put it together in a rod? What do you do with it after that? That just might be what tips the balance against, because everyone knows how to process oxides. It's not an accident that UO2 is the fuel of choice because it's a fairly stable material. You can pour it out on the bench. You don't need to be worried about it. There are, for example, reports that uranium nitrides are pyrophoric. So the last thing you need is your fuel bursting into flames, obviously for all sorts of obvious reasons. And again, that's just, you have to weigh up all the factors. You can't just hone in on one thing, which I guess is what you're alluding to.
There's a lot to consider there, especially.
I mean, I've been to see the production of the oxide at the Preston site, where it's basically this massive hopper. Yeah, it goes in at the top and it all comes out the bottom. Hugely mechanized, very impressive, but it relies on things not bursting into flames for a start, etc., etc. So if you had to retool a plant like that, that's a massive overhead. It's like in Dragon's Den when they talk about retooling their processes. It's all the costs that add up to something that's quite expensive already.
Absolutely. It's fascinating. Obviously, you're manufacturing a ceramic and the pellets are quite fragile. So the mood around the factory on these vibrating carpet tiles, basically, it's a fascinating process to watch. Yeah. Trying to have a look on the chat there. Don't think I've missed any other questions. I mean, talking about different fuels, it's interesting to note that India, because it's got abundant supplies of thorium, are exploring the thoria route. And I guess that's attractive because you don't need to enrich the fuel. You can just purify it and use the thorium, and it doesn't produce plutonium as a side product. Do you think, had we not had the military application of uranium, do you think we might have gone the thorium route, or is that a possible preferred route for the future, do you think?
That's an interesting one. I think thorium fuel cycles are quite interesting, right? Because they're nominally proliferation resistant. Although, correct me if I'm wrong, my understanding has always been, though, that what you get out the other end can actually be a lot worse than what you get from a uranium fuel rod. And so we're back to this holistic, what's the overall process look like? And if what you're dealing with at the back end is so horrendous that it's now impractical, all those good points, because clearly something that's proliferation resistant is a very good thing, it no longer matters. I think usually I think it normally comes down to who's blessed with having a natural supply, and then they run with that, because that tends to be a major contributory factor to your synergic overall holistic analysis. If you've got the stuff on tap in your own country, then clearly you've removed an enormous component from the cost base and introduced something really very practical to use. Because, you know, we've got what we've got. Then again, most of the uranium on the planet isn't actually in the ground, it's in the oceans. So then how do we extract it? Yeah, when you lift the lid on this tin of worms, you find tins of worms within tins of worms, and it seems to go on forever. And this is what makes it such a challenging thing to deal with in the round.
Absolutely, it's a fascinating subject, and you talk about what interests you in the field, and there are so many different aspects now and future opportunities. And you mentioned, I mean, the possibility of extracting uranium from seawater. It's perhaps as well, that might be something in the future that someone will have an efficient process to do. Who knows? There are many challenges associated with it.
Yeah, absolutely.
But it's interesting, the link you made with medicinal chemistry as well, because again, when people think of nuclear, and they don't realize nuclear medicine plays such a benefit to society, and without the research in the nuclear field, you wouldn't get this sort of nuclear therapeutic and diagnostic tools that we are very grateful for.
Absolutely, yeah. Because no one ever thinks about them, because it's very rare that you actually need such things, because you're in a bad place if you do, but then it could be the thing that saves your life.
That's true.
So actually, yeah, at the minute, I think the US is pushing actinium radiotherapy quite a lot. So there are some groups out there purely focused on this now.
Yeah. Yes. So it doesn't help with the medical profession rename something that's nuclear magnetic resonance as an MRI scanner, does it?
Indeed.
Excellent. Does anyone have any more questions? If you do, put them in the chat. If not, I'd just like to say thank you so much to you for your time and a really fascinating talk. And I certainly urge people to follow the outreach link at the end as well to find out more about Manchester's research as well. Jill, I don't know if you want to say a few words. So yeah, someone has suggested a virtual round of applause for the presentation. Really good stuff. So I'd like to certainly echo that.
Yes, I think we all should thank Steve. Thank you very much. It was very clear and some very interesting facts and points there. So thank you. So yes, a virtual applause is an excellent idea. Thank you.